Hello students, in today's lecture we are going to discuss about magnetostatics. So in previous set of lectures on electrostatics, our basic concern was to calculate the force experienced by a test charge due to a collection of charges which were at rest. So that's the important point. The charges were at rest. So naturally, the question arises, what happens when the charges are in motion? Now, when the charge is in motion, in addition to the electric field E, charges in motion also produce a magnetic field B. Okay, this is the important point. So you have the electric field. In addition to that, you also have a magnetic field if the charges are moving. So we are in the coming lectures. 4 or 5 lectures, we are going to discuss all aspects of this magnetic field B. We are going to calculate the field due to variety of charges in motion. Okay. Now, before we go into that, let's first discuss what should be the force experienced by a charge Q moving with a velocity B in a magnetic field B. So the magnetic field is already existing, and a charge Q is moving in a velocity V. So that the force which we call as F magnetic is given by Q V cross B. Okay, please pay special attention to this cross product V cross B. What it tells you that this force is perpendicular to both V and B. Okay, that's very crucial point to remember. The magnetic force is perpendicular to both V and B. And that has an immediate consequence. Since F magnetic is perpendicular to both V and B, what happens is that work done becomes 0, right? So that's very easy to understand. In fact, if you want to do it explicitly, you can see that the work done is nothing but F dot dl, and F dot in place of F you put Q V cross B, and then dl is nothing but your V into dt. So there is a cross product along with a dot product. So eventually with a simple vector algebra, you can see that it's 0. So it essentially means that your magnetic force do not do any work. Okay, so this is about if there is a magnetic field present. Now, if in addition to magnetic field, if you also have an electric field E, then naturally your electrostatic force also will come in picture. So the final expression, if you include both electric field and magnetic field, becomes F, the force is nothing but QE, which is the electric field part, and the magnetic field, B cross B part. Okay. Now let's take some examples to understand this magnetic force. So the first example, let's think of a charge Q, which is moving with a velocity B in XY plane. So let's think of this arrangement where your B is along minus G direction. Okay, if you look at this axis, and your charge Q is actually moving along the in XY plane along the Y cap direction. Okay, so now if it is in XY plane and moving along Y cap, so there will be a force which is V cross B. Now V cross B in this arrangement will point inward. So the force direction will be towards inside. Okay. So now since the magnetic force makes the particle drift perpendicular to its velocity of propagation, it will execute a uniform circular motion where the magnetic force provides the necessary centripetal acceleration. Okay, so if you want to write that, you can show F magnetic will be nothing but Q V cross B, and for this arrangement it is nothing but Q V B, where B is the magnitude. Okay, and the direction is of course minus x cap. Okay, so direction is inside. In fact, if it is here, it is minus x cap, and so wherever on the path it will be towards the origin. Okay, QVB. Now this is going to be sustained by the centripetal acceleration. So you can write the balance equation as UVB, nothing but your MV square by R. Okay. Now, so that if you rearrange, you will see that the momentum P, which is equal to MB, is nothing but QBR. So this is actually one of the way you can calculate this momentum of these particles, elementary particles, just releasing them in a uniform magnetic field. So the B is uniform here. Okay, if you measure, so you release these charged particles in this uniform magnetic field B and measure that trajectory, the R. Okay, so if you measure R, that will give you the momentum of these particles. Okay. Now we told that this particle is in uniform circular motion, right? In XY plane. Now imagine if the particle also has a velocity. So imagine the particle has a velocity component parallel to B. So particle also possess a velocity component parallel to B. Something like V parallel. So if that happens, so this velocity component will not be affected by, okay, it will not be affected by the magnetic field. So it will keep on executing the circular motion along with this component, right? Along with the velocity component V parallel. So in effect, you will have an helix. Okay, so this will keep on moving like an helix. Okay. So I hope you understand that. So this is how a charged particle behaves in an uniform magnetic field. Now let's put a little bit more complication in this set of problem. The same problem we take and we add the electric field also. So now we have the full both electric and magnetic field. So let's take a simplified situation where there is E along Z direction, B along X direction. Okay, both are perpendicular to each other, and a particle at charge Q is released at the origin O. So what happens? So this is the definition of the problem is the following. You have B, which is magnitude B X cap. You have electric field E along Z cap. So the position of the particle at any given instant will be 0, YT, ZT. So 0 meaning since, the magnetic field will not affect along this direction. So you will, so the particle will not have any component along X. Okay. Similarly, the velocity also along this X will also be 0. The X component of the velocity will also be 0. So you will only have the Y dot and Z dot. So dot signifies the dy by dt, right? You know that. So Y dot essentially dy by dt. Okay. Similarly, Z dot. So these let's call the velocity as Vy and Vz. So if it is 0 Y dot Z dot or 0 Vy Vz. Okay, so now if you want to calculate the force, you write down the total force expression along with the electric field and magnetic field. So here effectively you have to calculate the V cross B part. Now V cross B, here if you just write component wise, so X cap, Y cap, Z cap, and then you have your V component, that is your 0, Y dot, Z dot, Vy, Vz, and then the B component, which is only along the X cap, so you have only B 0, 0. And so if you calculate the determinant, you will have B Z dot Y cap minus B Y dot Z cap. Now this force, it will be nothing but like a mass into acceleration, right? And that you can express like M Y dot Y double dot Y cap, M Z double dot Z cap. So that will be your force, MA part. And the right side, QE is nothing but QE Z cap, and then B cross B have already calculated here, so that will give come like that. So you can write the equation of motion component wise. So you just separate out the Y cap and Z cap components, and you can write the following two equations. My double dot is QB Z dot, MZ double dot is QE QB minus QB Y dot. Okay. Now to make it a little bit more simplified, you can substitute something known as omega as QB by M. It is also known as cyclotron frequency. So if you substitute that, you will end up with y double dot as omega z dot, okay, and z double dot as omega e by b minus y dot. So these are the two equation numbers, and these are coupled differential equations. So how do you solve that? So there are some simpler way to do it. So what you do, you can think of a simple way, like you take substitute e by b minus y dot as some x. So if you do that, so let's say, let me just do it in a simple way. I urge you to calculate it at home. I'll just show you, give you some hints. So you substitute x as e by b minus y dot. Okay. So if you do that, what you will have, y dot you can write as vy. Okay. So let me first write this as in terms of vy, so it will be easier. So y double dot is nothing but your vy dot is equal to omega vz. Z dot is nothing but vz, right? Z double dot is nothing but vz dot is equal to omega e by b minus vy. That is your y dot. Okay, so from here I just wrote this one. Now you substitute your e by b minus, how to solve it? So e by b minus vy as x. So that's when you can put something like omega x. So if you do that, now you can see that if you say x dot will be nothing but, so x is e by b minus by. So which means x dot will be nothing but, so x dot will be what? It will be minus by dot, because x is e by b minus by. So x dot will be minus by dot. E by b is a constant, so it will be only minus by dot. And by dot is this one. So you can substitute from here by dot, and that turns out to be minus omega vz, right? Then you can do a further differentiation and put x double dot. So that will be, again, you do the same substitution. So you will end up with minus omega vz dot. Okay. Now that, if you substitute for vz dot from here, you will have minus omega square x. Please look at it. Okay. That's how it will come out. Now look at this equation. I'm sure you may be familiar with this set of kind of equation. So this is like d square x by dt square equal to minus some omega square, some constant x. So this has a very general kind of solution in calculus, and we can write the general solution like x equal to a sine omega t plus alpha, something like that. So this is a more general solution. Okay. So if you write that, now remember what we substituted for x. X is nothing but e by b minus by. So if you again do a little bit rearrangement, you find by is nothing but a sine omega t plus alpha minus e by b. Okay, like that. And you can also this we substituted for vz, right? So you can do the other way and substitute for by to eliminate vy, and that will give you an equation in terms of vz. Please check that. Now how to solve that? So you have vy and vz. Vy is nothing but what? Vy is y dot, right? So vy is your y dot, right? Vz is nothing but z dot. So now y dot is this. So you can do the integration, and you can find out. So first you can do a first you have to calculate the constants a, alpha, and other things, and for that you need the initial conditions. So the initial conditions. So initial conditions are at t equal to 0. your y0 equals to z0 equals to 0, and also by equals to vz equals to 0. So these are the initial conditions. These are the set of equations. So from there you can calculate all those constants, and if you do that, you finally will end up. Please check that. If you are not able to find out, we can do it in the tutorial classes or in the discussion classes. So the solutions, set of solutions which you will get for this is nothing but omega t minus sin omega t and zt. So I'm not going through all the algebra here. You please check that and see if there is a mistake here, but it will come somehow like this. Okay, cos omega t. So this is the solution. So you have yt and zt. So in principle, it can give you the trajectory of the particle. Your xt is 0 anyway, right, all the time. Now this again doesn't really make too much of a simplified look. So what we can do, we can again substitute a little bit with saying that r is e by b, e by omega b. R is, so you can check this. E is electric field, b is magnetic field, omega is frequency. So look at dimensionally whether this corresponds to length scale. So R is like a length scale. And also use the fact that sine square omega t plus cos square omega t is equal to 1. So just eliminate sine omega. So just take sine omega t left side and put everything on the right side and use this substitution. So this should give you y minus r omega t square minus z minus plus r square equal to 1. So this is nothing but a formula for a circle whose centers. So usually what happens, y minus let's say h square plus y minus k square equal to r square, right? This is how it comes out. And I think this is r square here. Yeah. So this is a formula for a circle with radius r and at center is at r. So center 0 r omega t r. So this is the center, and the center, there is a t component in the center at the y, so which means it moves at a constant velocity, which is omega r, and that's nothing but, if you look at this substitution, e by b. So it's a formula for a circle whose center moves at a constant velocity e by b along y direction. So we'll go back to our initial calculation, initial picture, and now we have found out that the trajectory of this particle is governed by this equation, which is nothing but a equation of a circle, and whose center is moving at a velocity r omega t. Okay, so if I do that, so this will appear like, sorry, let me put it this way. Yeah. Okay, like that. So this will be r, right? So this is how it will, and this is, so the center is moving, right? So this kind of motion is known as cycloid motion. Okay, so if you have any doubt on these trajectories, please ask questions in the discussion class. We'll discuss it further if you have any issue. But I want you to kind of calculate this, figure it out algebraically how it happens. Okay. So these are essentially coupled differential equations, and you have to solve it using initial conditions. Okay, now I'll switch over to another important concept. Since we are discussing about charges in motion, it is natural that we are discussing about, we should discuss about the current. So, and you all know the definition of current is nothing but charge per unit time. Okay, and the units are amperes. 1 ampere is essentially 1 coulomb per second. Okay. Now let's frame this definition in a slightly in terms of the charge densities, line, surface, and volume charge densities, volume current densities. So if you want to discuss about that, let's think about a segment of charge lambda in a line segment DL. So lambda is moving in a line segment DL, okay, with a velocity v. So the charge dq in this segment DL, so the charge for this segment DL is nothing but lambda in DL. Okay, so lambda is a segment of charge. Okay, you can think of a line charge density, and so you think of, so the charge which is in this so the charge which is in this segment is nothing but lambda DL. Okay. Now what will be the current? So current will be nothing but dq by dt. So this DL by dt will give you V. So current will be lambda into V. Okay. Please get familiar with these definitions. Now if current is lambda into V, so now we can calculate the magnetic force, which we know is nothing but, so since this is a segment DL, now if you want to calculate the magnetic force for the whole wire, you have to do the integration. And so the integration will comprise of B cross B, that cross product, okay, and the cross product, and dq. Okay, so you have to do the integration over the segments, all segments. Now what you can do, dq is nothing but lambda DL. So your V and DL, so you can take this. So V and lambda, you can see that will give you current I. So I should tell you that current I in general is a vector, but since the direction of the current is essentially governed by the direction of the wire in which it is flowing, naturally it will be not so kind of, apparent as far as the vector is concerned, but for a line segment it's easier to see. Okay, but current is in general a vector. Okay, and when we discuss about the surface current and volume current, we have to assign a sign. We cannot be no kind of, we have to be a bit strict about assigning a vector sign there. Okay, so now if you look at this calculation now, so what happens is that now we have V cross B lambda DL, and you lambda, you put it inside, lambda V gives you I. Okay, so lambda V gives you I. So finally you have an expression that magnetic force, if there is a current flowing, now I you can take out. If it is a constant current, you can take out I inside and just put DL into the cross product as a vector. So then that will give you I DL cross B. F magnetic is nothing but I, the current which is flowing through the air, and DL cross B integration. This is a very important expression, please remember. Now this is for a line charge. Now there can also be a current which is distributed over a surface, and for that we define something known as the surface current density, K, as di by dl perpendicular. So what I mean by that, so you have a surface, okay, so we have a surface, okay, some surface, and there is a ribbon you can think of, okay, and so this ribbon, some sort of a ribbon which is going, and this length of this cross-sectional length is nothing but dl perpendicular, this length, okay, this length is dl perpendicular, and if there is a current flowing K, so you assign a direction K. So now K is nothing but di by dl perpendicular. Okay. So that is for the surface current density. And if you want to write the magnetic force for that, then you have to, again, you have a similar expression here. So you will have K cross B dA. Now you have a area integration. So you are integrating over the area because there is surface current density. So the F magnetic for surface current densities are K cross B dA. So K is surface current density. And again, you can have a similar expression for volume current density. So in case of volume current density, you are thinking of a system where you have some sort of a, let's say some sort of a wire or some sort of a volumetric material. My drawing is bad, so let's say somewhere, okay, and in that you have a volume element. So a kind of a parallelepiped, which is going like that. Let me slightly draw it better. Okay. Okay. So now this is the cross sectional area. So now here you can think of this as a DA perpendicular, and the current is so there is a current density J. So then the definition of J is nothing but DI by DA perpendicular. Okay. So I is the current which is flowing through this, and J is the current density. I is the total current flowing through this. Okay. And if you want to calculate the magnetic force in terms of volume current density, so the expression now becomes a volume integral, integrated over the whole volume, and the integrand is nothing but J cross B deta. Okay. So now you have three kind of expression for a line charge density. So you have for a line charge, you have line segment, you have a magnetic as I dl cross B. For a surface current density, you have K cross B dA, surface integration, area integration. And for a volume current density, you have J cross B deta by volume integration. Okay, so just to kind of emphasize this more, let us just discuss a simple example. Think of a current I which is flowing in a wire of radius A. Now, if I ask you a question, what if it is uniformly distributed over the surface? So what is your K? Okay, so all I'm saying now, there is a current I which is flowing in a wire of radius A, and this current is uniformly distributed over the surface of the wire. So radius is A, so the surface is of the wire will have a circumference which will be 2 pi and A. Now your volume current density, sorry, surface current density, the definition says K is DI by DL perpendicular. So let me say K is DI by DL perpendicular, right? That's your, and I'll put the vector sign there. Now, if that is the case, now here, so your I will be K, okay, DL perpendicular. Since it is uniform distributed, you can take K out of the integration, and then you can simply DL perpendicular. DL perpendicular is nothing but your circumference. So that should give you 2 pi. If your radius is A, circumference will be 2 pi A. Okay. And that essentially means that your magnitude K, I mean, we can, because it's flowing along the wires, we can forget about the direction. So your K is nothing but okay. So K is nothing but I by 2 pi. Okay. So this is for a where the current is uniformly distributed over the surface. Now let us take up the second case. Let's say the current, there is a current density now, and which is proportional to the distance from the center. So S is the distance from center. So if it is a wire, if it is a cross-sectional wire, now this is your S. So at any point S, your volume current, so this wire is going like that. Okay. So at any point S, your J is proportional to 1 over S. So in that case, so now let us take the second case. So your J is proportional to 1 over S. Now, if that is the case, your I will be what? JDA, right? I is nothing but JDA. Okay. So I is nothing but, hold on. Okay, so I, what I was saying, I equal to J dA, right? So it will be J dA. Okay, and J dA is nothing but J is what? Let's say J is proportional to 1 over S. So J, you can think of something like alpha by S. So alpha by S. dA will be what? So for this, the surface will be what? dA integration will be S ds. Okay, that's your, so you think of the surface, the cross-sectional surface, right? So this should be S ds and then d phi. Please check that. So this is the integration, and that should give you SS goes away, ds should give you alpha comes out, and so this should give you 2 pi alpha a, right? Yeah, 2 pi alpha a, and from there you calculate the alpha, and that finally you should have J equals to let me remove this one. Okay. Finally, J should come out to be, so 2 by alpha I, that is your I. So alpha will be equal to I by 2 pi A, and J, so that should give you, imply J is nothing but alpha by S, right? So your I by 2 pi AS. So this is kind of two small examples of how to deal with surface and volume current densities. Now we will do more problems in the discussion classes. I'll show you, particularly this problem I'll show you in the discussion class, if there is a current loop and what happens for the force on the current loop. We'll see that, okay? Yes, so okay, in the next class we'll discuss about Biot-Savart's law and its applications.